Okay, we are ready to get started. We are here with one of our Geo-Legends, Dr. Mark Randolph, and we are going to be interviewing Mark about his career and how he got to be a Geo-Legend. So Mark, I'm going to start off with geotechnical engineering. You didn't study geotechnical engineering as an undergraduate, according to your Geo-Legend interview article. What attracted you to geotechnical engineering?
Well, it's hard to say. I think I just sort of fell into it by a whole series of circumstances. When I did my degree in Oxford, I was sponsored actually by a branch of the Ministry of Defence, the Army in the UK, but the civilian side of it, who really wanted to train engineers, mechanical engineers. In fact, initially I was going to read mathematics at Oxford, but they wouldn't give me a scholarship unless I read engineering. So I said, what the hell, let's read engineering. And Oxford is a general course, all branches, and I took one special paper in civil engineering and did a project with a structural engineer called Edgar Lightfoot on warping of beams. And then, the project went quite well, and we got friendly. And when I left, he said, "There's this new topic called critical state soil mechanics. It sounds rather interesting." And so when I left university and I asked to be put in a civil engineering environment, they ended up sending me to the building research establishment at the time of which John Burland was head of the division. And so suddenly I found myself in a geotechnical engineering environment and had a bit of catch up to do. But under John's guidance, that went very well. He put me out in the field in a couple of different projects with a guy called Arthur Marsland. One looking at the seawall defences in East London, and one doing pressure meter and other tests in the field and analysing the results. So I had to sort of hide a bit my lack of knowledge, and maybe I still don't understand some of the sort of subtleties of soil mechanics, like the Casagrande A-line and things. Well, what's this about? So I have to bluff my way through on occasions. That's true.
Yeah, well, I'm struck by how much you rely on self-learning and not having necessarily taken a course or been taught something, but you teaching yourself that subject matter. Can you talk a little bit about that? And is that true outside of geotechnical engineering in your life?
I think it is. Of course, nowadays with the internet, it's so easy in that respect. In my day, it was reading from books, and again, I can sort of partly blame the Oxford undergraduate course, because in those days, it's different now. The tutorial work, the example problems that you do and so forth, those were out of sync with the lectures. So you'd have tutorials in a topic that you hadn't covered in lectures, and so you had to read up from books and then work out how to solve the problems. And so I got used to learning as much from the library and treating the lectures more as social events. And of course, to me, that's really important as an aspect of university life, is actually the collegiate socializing with your peers, and talking through problems and so forth. But since then, I guess it's been natural to me to, if I need to find out about Bessel functions for a solution, I get a book on Bessel functions. So I just need to find out about real soil mechanics. I dig out an old copy of Tazargian Peck and start from the grassroots again. Yeah, and of course nowadays you've always got AI there to help you sift through not always the truth, but at least to like a pinball machine, you work your way more towards understanding. And I think that's a really important aspect of life, and not being daunted, but just continually growing. We're students all our life.
Yeah, it's humbling too, because every time I go to learn something, I realize how much I don't know. And the more that's accessible, like today with the internet, the more I realize how far I have to go to learn everything. So yeah, it's a great lesson for our students that they constantly need to be learning and not passively waiting for somebody to explain something to them. I'm curious. So you have always struck me as very theoretical in a sense, and you're an expert in mechanics and really strong with math. And yet you thrive in geotechnical engineering, where it's as much based on experience and judgment and empirical evidence as it is theory. So can you talk a little bit about that and how you balance all of those factors?
It's an interesting question, because I suppose growing up, I grew up in the country, and in the country you fix things that go wrong. So the first thing you have to understand is, why is it going wrong, and then you fix it in a practical way. In soil mechanics, I've always tried to think, this is a real physical problem. What's driving it? What's if you like, a worm's eye view of what is happening in the soil that leads to an event? I mean, recently I've done work on pile run, where the pile just takes off and plunges into soil that on the face of it is too strong for the pile to move. So what is happening? How is it being destroyed on the fabric as the pile advances? And so you then try to come up with not exact, but mathematical or phenomenological models that seem to reproduce the event. And so to me, when you do research, whether it's physical modeling or numerical modeling or so forth, it's like gathering data. How did this perform? And in the modern world of machine learning, you throw all the data at the model and it would come up with something. But so I suppose my equivalent is to learn from the data, to synthesize it. It may involve curve fits. It may involve actually a little mathematical model that reproduces that result. So I think everything can be modeled to a degree, whether it's just a 3D finite element computation or whether it's a neat algebraic model. I suppose my interest and my aim is to go for the latter, the little neat algebraic model, even if it's not perfect, rather than rely on endless numerical modeling.
Right. You've talked a bit about Oxford, but I'd like you to explain to the audience just your journey from starting at Oxford, and then you were at the geotechnical division of the Building Research Establishment, which is not maybe known to many people, with John Burland there. And then you went to Cambridge after that, and not only studied at Cambridge, but you were on the faculty at Cambridge for a bit. So can you talk about that part of your career?
Yeah, so I guess so it all started, as you say, at Oxford, and I met my wife there during the first year. We got married at the start of our second year. Well, that sort of all sorted out. I think we've been a pretty stable relationship since then. And so when I graduated and went to work at the Building Research Establishment, and John Burland was a great sort of mentor at one step removed. He wasn't my direct manager, but he knew who I was, and he encouraged me at that stage to think in terms of at some stage doing a PhD. And of course, John has a close association with Cambridge and with Peter Roth, and so he encouraged me to make contact with Peter. And so I think I was at BRE for maybe 2 years before I was permitted to, we planned for me to have a year's break from BRE and spend a year in Cambridge starting a PhD with Peter Roth. So that was in 1975, I guess. October 75 it started. And so Cambridge, of course, there was Peter Roth there. Andrew Schofield was the lead professor in soil mechanics, and so was another of my future mentors. And so it was a very live place, and many PhD students, and sort of a very active group working. So we like to think at the sort of forefront of new soil mechanics. So it sort of progressed from there, and so I spent a year in Cambridge at that stage, then a year back at the Building Research Establishment, since doing just mostly pursuing my PhD, a little bit of other work with projects that came in, and then I suppose I applied and got a research fellowship during my third year of the PhD. That's what they call a junior research fellowship at St John's College, and so that meant that I could leave BRE and have a salary at Cambridge. So I made that move and submitted my PhD, and then that research fellowship, I applied and was elected to a teaching lectureship in the faculty, and that changed my status in the college to a sort of teaching fellow. And in due course, I got tenure there. So I did 5 years probably as a junior lecturer, assistant lecturer, that's what you might call it, and then got tenure. And I think it was that getting tenure that made me move. So that was the sort of so I was a lecturer there from, I guess, 1978 to 1986 before we moved to Australia. So it was a sort of gradual progression, but of course that's a short account of many things that happened during that time. But like much of life, nothing was really planned. It just evolves, as you know.
Yeah. I want to rewind to when you were at the geotechnical division of the building research establishment, because if you were there when I think you were there, wasn't there a big drought in the London area in the early 1970s to mid 1970s? And it seemed like John Burland was doing a lot with expansive soils and problems with foundations because of that drought. Were you a part of all of that?
I wasn't directly. I was interested because I ended up living in a sort of I don't know, 80-year-old cottage in Cambridge on these galt clay soils that were shrinking and swelling and seasonally. So I could see it all happening around me with trees too close to buildings and drying up the ground and the buildings moving. So I guess with brick buildings on clay, you get used to it. It's a bit more disruptive if the damage gets too bad and you get gaps appearing. But so many buildings big buildings are cracked because of these shrinking soils. In fact, interestingly, when I just jumping ahead, but when I moved to Australia in 1986, I had this phone call out of the blue from South Australia where they got similar soil conditions, and I was taken out. I flew over to Adelaide to do some consulting where they were creating these so-called waffle pad foundations to stiffen up the foundation slab for the building, and so I had to again use previous experience and a lot of John Burland's work to help me with that. So I've never really, I suppose, done much in the area of unsaturated soils and what happens during this process, but I've read quite a lot about it because it's an interesting topic.
Yeah, and where I am in Austin, Texas, we have all sorts of the same. In fact, our soils, when John Burland was here, he was taken aback by how similar our soils are. In fact, they're the same geologic origin as what you have in the London area, these highly plastic marine clays, which you have gotten to work quite a bit with now that you've done all the work that you've done offshore, where we have a lot of these highly plastic marine clays in a different environment where we're not worried about shrinking and swelling necessarily, but the same mineralogy and the same types of materials.
And really high plasticity indices and things, yes.
Yeah. Okay, and before we get to Australia, tell us about Peter Roth as a mentor and an inspiration for you in your career.
I can see how Peter Roth and Andrew Schofield were sort of not exactly chalk and cheese, but they sort of balanced each other in terms of personalities in lots of ways. If I was to paint an extreme, Peter Roth was the more schoolmasterly, working through the process and sorting out ideas, and was Andrew was the live wire with the slightly uncontrollable touches of genius. I think that produced a lot of the ideas. So Peter was a. I mean, he taught me so much, which I still try to pass on to my own PhD students. Of, when you write something, make sure you are writing exactly what you mean to say. That the clarity of expression and writing, he emphasized not just as grammar, but make sure that the subject agrees with the noun, with the verb, and the object, and is exactly what you're trying to express. So he would tear my drafts to shreds. No, in a nice way. He would come back and point out these aberrations. And I remember watching him in a lecture, in any lecture, if it's a sort of seminar, he would start with a blank piece of paper and a pen, and he would make these fantastically clear notes and little sketch diagrams. I can recognize a Roth diagram from 100 meters these days, just the style of them. And I asked him, I said, it's impressive because I tend to scribble and doodle and all sorts of things in a lecture. And he made the point that you may not even keep those notes, but the act of writing things down process the information through your mind in such a way that it retains a bit more, and so that side of things, it was a lifelong learning skill for me to understand. I mean, it didn't change my ability to write notes, but I understood why one does it. But of course, Peter Roth was much more than that. He had several very interesting research directions. Obviously, the self-boarding pressure meter was big on his horizon in those days, but he also changed my career path in terms of geotechnical engineering in terms of pile foundations to into the offshore arena. He had a project with Amoco in the States, it was then, with a very interesting character called Ben Murphy, who of course is no longer with us. But through that and the meetings that this is the ESAC project, it involved through that I got to meet Don Murph, who's been another big factor in my offshore geotechnical life. And I'm not sure the ideas we put together in that project necessarily withstood the time, but I think we had an idea to try to move towards some effective stress model of the axial capacity of piles, which I think laid the groundwork for future works, trying to bridge the gap between a pure empiricism and a more scientific approach, which we might come back to later. So that move, and through that, of course, having through that project, I then started to make contact with geotechnical engineers in the London-based BP, and sort of started working a little bit with BP in London. And then through that, of course, with the first major gas project in Western Australia, North Rankine, had piling problems, I got involved with that. And so it all started with, as Peter Roth's introduction, and traveling with him to the States, and giving very poor, no doubt muddled presentations, but under his mentorship, gradually improving. So,
that's fantastic. Yeah, and that's a great transition into the next part of your career. You spent 34 years on the faculty at the University of Western Australia. You're a member of and I won't get the names exactly right, but essentially the Academy of Science and the Academy of Engineering for Australia, and you're also a member of the same academies for the United Kingdom. So you've been extremely successful both at the United Kingdom and then in Australia throughout your career. Can you talk a little bit about that move from England to Australia and what motivated you to go down under?
Well, this is 1986. We dipped our toe in the water of Australia a couple of times. I had in 1980. 1980. We went out for 3 months. I had a sabbatical trip to the University of Sydney, where, of course, I got to meet and work with Harry Poulos, but also very influentially met and worked with John Booker, and we had a ball. We lived on Glebe Point Road. It was close to the university, and we appreciated the Australian weather, and we had a little VW that we drove up to Brisbane to see John Carter at some stage. So it was a sort of we realised how interesting and different Australia was and could be. And then I had a bit of consulting on the North Rankine project, and part of that brought me back in 1985 for a week in Perth. And then we spent a few more weeks in Sydney working with what was being hosted by John Booker there. And during that week in Perth, two faculty members, Richard Jewell and Martin Fahy, both of whom, well, Martin Fahy I ended up supervising the last year of his PhD in Cambridge, and Richard Jewell had visited, so I knew them both, and they knew me, and they said, what would it take to entice you to take a job out here? And you look out the window and you see the weather and you think, well, not very much actually. So anyway, as a family, by that stage, we had 2 young boys. And I think my wife Cherry was not totally comfortable in the rather misogynistic environment in Cambridge, especially in some of the colleges. And we looked at each other and said, what's the downside? We could have 2 years in the sunshine and come back and I'll get another job. So we uprooted, not as many people at my stage at Cambridge might have got a chair in some provincial university. I just went out as a senior lecturer to this unknown University of Western Australia, knowing that there was interesting consulting to be done. There was a great climate, and let's just see how it goes. And so we did, and I think we never looked back, really.
Oh, that's really great. So you've raised the issue of your family. Can you tell us a little bit about your family, your wife and your sons?
Yeah, so as I say, I met Cherry. She was one of 4 female undergraduates doing engineering in my year at Oxford, 4 out of 100. But we seemed to get on pretty well in terms of just being friends for a while, or just colleagues. I actually got to know a little bit the people who were tutoring her, and so our lives sort of gradually moved together, and we decided that we got on well together, and we decided to get married, say at the start of our 2nd year, and move out of college, out of rented accommodation or college accommodation, into our own apartment. And so at that stage, Cherry was pursuing a more systems analysis, sort of business systems, if you like, in engineering. She was also, let's say, reading engineering, but moved more towards the electronic side, if you like. And then got her first job with Kodak as a systems analyst. And so she then moved to a job in Cambridge when I moved there. So she worked for Philips, and then for a small startup design company, computer aided design. And so then after a while, we had first one child and then the other. So Nick and Tom were both born there when I think when they were 6 and 8 when we moved to Australia. They'd already visited twice, I suppose. It was unusual. One when Tom was 3 months and Nick was just under 2 years, or 2 years. And then say we again in 1985 when they're a bit older, and then we moved when they were say in just at the start of primary school, really. And I think because they were different, they were English and very un-Australian. So, but they morphed as children do. They soon learned the local vernacular and fitted in. And I think on the move out, we Cherry and I both took sailing lessons, just dinghy sailing lessons, because we thought we're going to Western Australia. We've got to be familiar with the water. And although we've never pursued sailing per se, both the boys went through dinghy sailing, and Nick got to quite a high level and was sailing Olympic class 49ers and things by the time he eventually called it a day. And so it's and of course on the way there's a bit of surfing and so forth. So we became an Australian family, and I think we took out citizenship within 3 years and just felt comfortable. But one thing that's interesting in terms of family is that by the time we got settled in Australia, both our mothers were still alive, but our fathers had both died. And so our mothers used to come out to visit us for typically 6 weeks, say, quite an extended visit. And I think during those visits, we got to know them, understand them as people, rather than mothers, so much better, because you just sit in the evenings and you talk about life and the family and so forth. Whereas when we're in the UK, you go and visit. You pile into the car, you drive 3 hours, and you spend the weekend with them, and you never really have conversations. So this idea of extended visits from over a large distance was actually, to me, brought us both closer to our parents in those days.
Yeah, that's a really interesting insight. So you can't just come over for dinner in Western Australia. If you're going to visit, you're going to be there for quite a while.
For a while, yes.
Yeah, and that gives you a great opportunity to learn people better. I agree with you. I got to know my mom only after my dad passed away when she moved to Austin, and instead of us visiting, we were living in the same place, and I could really get to know her more as a person at that point.
Yep.
Yeah. Well, speaking of your family, tell us about Mount Kilimanjaro.
Well, I suppose I'm regarded pretty much as a workaholic. I'm endlessly full of ideas, and I spend a lot of time looking at my computer screen. And so one of the ways of going on holiday without a computer is to go bushwalking. And so from about, I think, 1995, I think, when the boys were old enough to be left on their own and do their own thing, we decided to go and walk across not the middle of Tasmania, but do a multi-day sort of 6-day walk called the Overland Track. And in those days, we were ill prepared. I think we were not totally clueless. I think my wife grew up as a girl guide in the UK and was pretty skilled in sort of bush skills. But anyway, so this became our typical holiday. Is we would go on multi-day walks with a full pack, carrying all our food for 7 to 10 days. And in fact, the background to my screen background here is taken from we found ourselves privileged to walk in the north on the Kakadu Plateau in the north of Australia, which is just incredible rock country and billabongs, and just impressive actually as a terrain. And then so I still play tennis, and my tennis partner, not really a bushwalker, but he said, "Hey, Mark, have you ever thought about climbing Kilimanjaro?" I said, "No." He said, "Well, why don't we do it?" So he and his partner Diane and Cherry and I did a little bit of training, not very much, but we picked a day which was a full moon at night, actually on Australia Day, January the 26th, to do the climb, and we took a deliberately one of the longer routes, Rongai, to help acclimatize. But it's still, yeah, I still class it as the toughest 5 hours of my life. That's going from, you start at midnight-ish, you have to climb 1,200 meters from, I think, 4.7 up to 5.9 is the but you get up to this volcanic rim first. So that's the big step. That's the 5 hours. So you have a snack at about 11 o'clock, and you put on 7 layers of clothes. It's bloody cold out there. and you just then you trudge, and we all had head torches, of course, but it was light enough by the moon to walk up, and our very experienced guides had a nice slow steady pace, and we just plodded for 5 hours and eventually ended up on the rim, the volcanic rim. Forget the name of the little place that's the name. The guide looked around to us. We were pretty exhausted. Our water bottles are frozen, but we had one thermos flask with warm water in it, so we shared that around. And he said, "Oh, well, are we fit to do another 2 hours around the rim to the top?" And he looked at Cherry, who was sort of looking a bit withdrawn. He said, "You bet, we got so far. We'll not stop it now." So we did it. So we got up there in reasonable time. I think took about sort of 6-7 hours, and froze at the top. Quick picture, and then the guide said, "Look, a few photos, but then you're coming down quickly, because if you stay up there too long, you're not used to it." We'd done other high altitude walks before, but that was actually the highest we'd been. I think we'd been up to about 5-7 before. I guess it's sort of -15 or something. It's quite cool. And you come down, long time to climb up, but you come down a scree slope. So just loose gravel pebbles and small sand and stuff. And so you let yourself slide. Each step you're covering about 2 or 3 meters, so you pace and slide, and so you come down the first part really fast, and then of course you walk out, eventually getting down to. So I think you drop about 2,000 or 3,000 meters on the way down over the course of the day. You get down to base camp, have a sleep. But no, don't get a sleep. You have a rest for an hour, then you move on. So it was I wouldn't say one of the greatest walks in terms of scenery, but it was it was tough and a sort of great feeling of achievement, I suppose.
Yeah, that's really, really impressive. Wow. And no computers and no internet and
no computers. No, you sort of look back and think, did we really do this? It was 2013, so we were early 60s then, and I wouldn't want to do it now. Although having said that, I think in January we're taking our grandson, who's 14 and accompanied by his father. We're doing the overland track again. We've done it 2 or 3 times in Tasmania. And that starts with a pretty tough climb for at our age. So we'll go slowly and hope we survive. So it's been our life, and we try to get out once or twice a year to do mostly day walks these days, but a few longer ones.
Yeah, that's great that the next Randolph generation is getting involved in that as well.
The rite of passage, that's right.
Yeah. Okay, let's go back to the University of Western Australia. What I know of your program is the Center for Offshore Foundation Systems that you created. Can you tell us a little bit about what that center is and also how you built this center?
Well, when I moved to UWA, we slightly it was a fairly sleepy place in terms of research. There hadn't been any PhD students in the group for a couple of years. And so we started trying to attract PhD students there, especially from the UK, because it's there's a link between Australia and the UK, and you've got a big climate change, so it was quite easy to attract both British and Australian students to do a PhD. And so we started building what we call a geomechanics group, and started keeping records of grants we got, consulting we'd done as a group, and started actually developing the infrastructure, which when you apply for grants is very important. one of the first things that I learned actually from Lyman Rees when I visited is to build your portfolio as an academic, but also as a group. And so we started doing those things, and then we just got, we'd been very active in the offshore field with North Rankine and the next platform, Goodwin. And John Carter from the University of Sydney had also worked on those projects. And so we applied without much expectation of success to what in those days was really the golden prize within our Australian Research Council, which are these 9-year-long, $1 million a year grants to have what they call a special research centre. So we put this proposal in for a special research centre in offshore foundation systems. We'll come back to that name in a moment. And by some miracle, we got lucky and were awarded this grant. It comes in 3-year review cycles, so 3 times 3 is 9 years. But you can't get these long platform grants these days. The most, I think, is about 7 years these days. So it was a good time, and that enabled us to, in a sense, do longer-term blue sky research as well as the day-to-day studies you need to solve today's problems, as it were. And with that, of course, you got seed money, but you attract postgraduate, junior academics to kind of work with you, and that attracts PhD students. And one of the centerpieces for our group in Australia was the centrifuge that we installed, and we'll come back to that a little later. But so we were very big on physical modeling, which is, of course, you need data, and in offshore you can't get data directly, so you have to create it in your experiments in the lab mostly. The other sort of consideration in choosing the name was it needs to be offshore. We could have called it geotechnical engineering, I guess, but it also has to have an abbreviation that you can articulate. And if it was a Centre for Offshore Geotechnical Engineering, Koji, how do you pronounce Koji? We have a Koji Beach, but that's COGEE. So we thought COFS, foundation system, that works. It's short, it's abrupt, and it's a cachet. So that's how it became foundation systems. And of course, foundations in those days was driven piles or drilled and grouted piles. But through the years of the centre, we've morphed into pipelines, anchoring systems, suction caissons, the whole gamut of different types of things that interact with the seabed. And of course, also devices that push into the seabed. So we sort of we try to cover anything that might touch the seabed in the name. And that was started in 1997. So it's still surviving to this day, but probably it's I would say it's close to done its dash as we move more into offshore renewables. But it's certainly been a fantastically fun period of research for us, and a very good corporate spirit, group spirit in the group. That's I think we generally are very collegiate with each other and treat each other with respect and share ideas and co-publish and things. So it's been really for me an absolutely ideal life research model.
Yeah, it's a wonderful place that you created, there. Not only is everybody really nice and supportive, and I interact with the people from your university all over the world, and they're still really nice, even if they're no longer part of the University of Western Australia or COFS, but they're also extremely talented. You attracted a group of really, really bright, creative, talented individuals that all got along and were supportive of one another, which is a rare thing.
Yes, I think I remember being reminded the other day about we used to have these annual workshops, maybe 1 or 2 days, where we'd sort of share ideas and look back on the year and look forward. I remember being reminded of starting one by asking the question, "Are we having fun?" And that's the sort of a core that the idea, the ethos was to have fun, to share things, and to not be threatened by other research going on, but actually collaborate. And I think through sharing, you build. You do better research, and that's certainly been at the basis of our group for many years now.
Yeah, well, it worked. You created something really impactful and powerful. And I am struck by your answer. You said you backed into foundation systems because of the acronym, and yet when I think of you, I think of systems, and not just piles, but piles that are connected to rafts, or not just anchors, but anchors that are part of a mooring system, and they're all interacting with the structural system as well as the ground in their behavior. So I find it funny that you chose that name not because you were thinking that's what it was going to be, but because it worked as an acronym.
Well, I don't know whether it was exactly that, but it seemed to work, as you say, in lots of different ways.
Yeah, yeah, that's great. Well, so the one of the reasons you went to Australia and one of the biggest challenges that you've dealt with throughout your career are calcareous soils. Can you tell us a little bit about calcareous soils and why they're so challenging and some of the ways in which you've managed those challenges?
Oh, yes, because the distinguishing feature in different degrees is the angularity and the crushability of calcareous soil. And on the Northwest Shelf, we have quite an extreme version of silty carbonate material that's very, very angular. They're just decayed shell fragments, shell animals on the micro scale. And so if you can imagine a pile being pushed into these soils, you have a crushed zone on the outside, which is sort of typically about the width of the wall thickness of the pile. And there's an arch in terms of stresses around that zone that just holds back the effective stresses so that you've got very little contact with the pile. And that's the basis why driven piles don't work so well in our particular type of calcareous soil deposits. Of course, you do get cementation there, so you can have some of which are connected with sea level changes, and so you'll get maybe a 2 to 3 meter thick layer halfway down that might be quite strong material where you can't push a cone penetrometer through. And then you'll go back to soft material, and then eventually you get into a weak limestone with I guess a typical cone resistance that you might, if you're lucky, be able to push into it. So quite a weak 1 or 2 MPa UCS material. And of course, other parts of the world in the Middle East, you've got less crushable calcareous deposits, carbonate deposits. In Brazil, you've got rather similar material to our environment. So although it's crushable, it's also very frictional. So you've got it's friction angles that start about 40 degrees. And so you've got the basis for strong bearing capacity, but at the expense of quite a lot of movement as that foundation settles. So shallow foundation, mud foundations will work quite well on these materials, but they will settle. The consolidation settlement will be large as the material just compacts beneath it. So I think you try to choose your foundation approach to accommodate these different aspects of carbonate soils. And of course, one of the pushes to understand the material better was to try to develop field devices that could capture both the intact condition, but also what happens when it's remolded. That was the basis of developing these penetrometers. First of all, the T-bar, the horizontal cylinder, like a croquet mallet that you push into the soil, and in principle, the material flows around the cylinder from the bottom to the top as it's advanced. And then as you withdraw it, the reverse happens. And in that zone, you're creating a pocket of remolded material in situ. And so that we started in the laboratory, proved it in the field, but it's been a core of our model testing, centrifuge model testing, is to be able to have a miniature T-bar or ball penetrometer that we push into the soil and measure the in situ properties. It's got a fairly well, it's got smaller corrections and a better defined bearing factor than the cone penetrometer, so it worked well for us, and I think it's still used extensively in the field.
It is, and we now use it for all sorts of soft materials, not just calcareous materials. And what I'm always fascinated by is your approach to it. And I might be misunderstanding it, but I'm going to give you my understanding of your approach to it, which was, why not create a shape that the mechanics are easy, so we can analyze it and understand what we're measuring, instead of what we typically do is we've got some kind of shape that somebody's produced for whatever reason that works like a cone penetrometer that isn't very simple at all in terms of the mechanics, and there's all sorts of boundary conditions and other issues you have to deal with in understanding what's going on. So I thought it was really clever the way you came up with a ball and a bar that got rid of all of those artifacts that make it difficult to understand.
I think that's right, and that was certainly at the back of our minds with initially the T-bar and also the spherical penetrometer. And of course, it's not quite as neat and nice as you had hoped, because as you push the device in, the material is already starting to break down and remold, even in that first path. And so there are adjustment factors. And of course, you also then start focusing on, hey, this is quite high strain rate. If you look at the strain rate around the bar compared with what it is in a laboratory triaxial or simple shear test, it's 3 or 4 orders of magnitude higher strain rate. So what do we do about that? And so all these adjustment factors come in, and you sort of come back eventually to the number you first thought of, but not exactly. And I had the pleasure of a long multi-year project led by Tom Lune at the Norwegian Geotechnical Institute in Oslo, where we again attracted sponsorship from a wide variety of oil companies, offshore companies, and contractors, site investigation contractors, and obtain data and samples from all over the world to try to see, well, from a practical point of view, what are the factors that relate the penetrometer resistance to a laboratory test, and how does it change with the plasticity of the soil, West African clays compared with lower carbonate, lower plasticity index soils. And so that was a fantastic project that I think, in a sense, allowed us to home in on a narrower range of bearing factors that should be applicable.
Yeah. Well, it's been really impactful what you've done, pun intended, because we're using it all over the world in all sorts of different types of soils as the benchmark to understand what the resistance is for foundation design. Your career in offshore energy spans starting in hundreds of meters of water to we're now in thousands of meters, so an order of magnitude increase in terms of the water depth, and now we're going into renewable energy versus oil and gas. Can you tell us a little bit about what lessons you've learned along that journey?
Yes, I think well, life's about having fun and new challenges, and so the transition from what I call shallow water, so up to 200 meters water depth, where can have a fixed structure, to deep water, where you have to have some form of floating structure and anchors. As you go deeper, you introduce all these new problems. You're looking at anchoring systems rather than piles. The anchors may be a pile, but they may be a suction caisson. They may be a drag anchor. You're looking at long distances of pipelines laid in soft material, laid down canyons, and that where you may get intermittent geohazard events of a submarine landslide that could obviously apply forces to the pipeline and maybe break it. So a whole new range of problems that I guess our group has, I wouldn't say dabbled in, but confronted and done work along with other groups around the world to try to bracket solutions for these. And certainly things like suction caissons where they've been driven by all the work at NNGI, and that applied very successfully as anchors around the world. But we've also developed tools to try to understand their behavior and their capacity. And then, so that's still ongoing. I'm still involved in projects that are dealing with the debris flows and modeling the debris flows and the forces on pipelines and so forth. And yet, we're also now looking at monopiles being 10, 11 meter diameter monopiles being driven into not just North Sea sands, dense sands, where now well-developed technology, but into new soil types, Taiwanese silts, where these things can free run over tens of meters unexpectedly. You're looking at nearshore deposits that have got boulders in amongst glacial clays. What's going to happen when you hit a boulder? How much damage will it do? Will it stop the pile moving? Will it damage the pile? So again, a whole new range of problems that you get a phone call and an email saying, are you interested in looking at this problem, you think, gulp, that's something totally different. And so, but of course, the idea is that on the research side, you try to anticipate these problems, and you hear stories about where the developments are, and you start trying to do some research in that, and then you hope you've got a little bit of understanding before the consulting job may come in. This is not, in my case, not mostly personal consulting. It's done through, well, initially through a company that we set up called Advanced Geomechanics, that was led by Mohammed Khorshid and then by Phil Watson, who's now back at UWA. But then eventually that company got bought by international geotechnical investigation company Fubro, and that's through. So I worked through that company mostly, which of course many of my former either PhD students or other colleagues from UWA, amongst many others, are still there. So it's a pleasure. It's like an extended family that you still see familiar faces there. But yes, the problems are wide ranging. Some companies are still very much into some countries are still very much into oil and gas developments, and others are more now focused on offshore renewable energy.
Yeah, those challenges are what keep it fun.
Yep, indeed, yes.
So I'm going to ask you a question that I didn't send you in advance because a student just asked me this in my last class a day ago. Do you regret having worked for the oil and gas industry because of the impacts of carbon-based energy on the world?
I don't think I have any regrets. I guess certainly initially you go into this not really understanding the consequences, and I think only over the last 5 or 10 years of the negative effects of even gas started to become more of a focus, and no doubt in my mind very obvious. So, and as we hopefully transition away from fossil fuels towards renewables, I think we're still going to have to rely on gas for a number of years, whether it's 30 years or more. I don't know. That's for the I guess it's a much bigger political question. Whether I'm comfortable still working on offshore fossil fuel projects, I guess I'm less comfortable, but of course they're interesting, and the work will be done. And that's a weak answer, I know, because like if everybody decided, no, you're on your own, if you want to do that you sort it out, then that could change things. But I think that's unlikely to happen. So I hope to move more and more towards the renewable type projects in the work that I do. But I suppose I'm at a stage where I have a body of knowledge that could be useful, and I'm happy to share that.
Yeah, and I expect that much of what has been learned is going to enable the ability to transition in the future. So you can't start from scratch. We're going to make use of everything that has been learned to be able to do better things going forward.
Oh, indeed, yes, indeed. And a lot of the models we've developed for, cyclic lateral loading, for cyclic axial loading, that they're all extremely relevant. The understanding of the soil types, the site investigation tools we have. That I think the whole knowledge base is now being applied as much as possible to the offshore renewables, and the design of anchoring systems and monopiles, What's in a size? You go from 3 meters up to 10 or 11 meters, and it's just a bigger object, not driven as far. And so the failure mechanisms are different, but it's still basically some form of pile foundation.
Yeah. You just reminded me, I don't know if I've ever told you this story, but in sometime around 2006 or 7, I was meeting with you and you asked me about the levees and the flood walls in New Orleans and how they had failed during Hurricane Katrina. And you were asking me, why don't they baffle them? Why don't they increase their moment of inertia essentially so they've got better bending capacity and bending stiffness? And I happened to the next several days be playing soccer with some geotechnical engineers here in Austin who were working on a project downtown Austin where they had to build a retaining wall right next to a railroad track. And the railroads are notoriously demanding about making it so there's almost no deformation at all. And so they had this design, which was an enormous row of drilled shafts. They were like 12 feet or 15 feet in diameter drilled shafts to be stiff enough to meet the railroad's criteria. And I said, well, why don't you baffle this wall so that it's going to give you that stiffness without having these enormous drilled shafts? And that's what they did. So every time I'm in downtown Austin and I go by that wall, I think of you. And I smile.
Well, of course you may make these comments not really understanding the magnitude of the task. These are long structures. They go for miles along the levee structures, and so there's a lot of inevitably a compromise between what you can put there. But certainly, the stiffness would help limit movements on the other side. Certainly.
Yeah. Yeah. Well, I'll make sure that Brad gets a picture of that wall so that while people are listening to this interview, they can look at it and think of you, Mark. Okay. In 2003, you gave the Rankine Lecturer, which is like one of the highest honors that you can receive as a geotechnical engineer in the world. And your lecture was around the role of empiricism and science in geotechnical engineering. Can you talk a little bit about that role of empiricism together with science?
Yes, it comes back to some of the earlier comments we made. I guess there's always this wish to try to close the gap between a design model based on science and calculation and the data that point in one direction, and they may not point in the same direction. So it's a geotechnical problem. There is something that tells you why the soil and pile behaved in a certain way for these soil conditions. And so if you could only understand what's the processes going on, then you can move forward to try to have a solution that uses this soil characteristics, but actually gives you a computed answer. And I think over the years, in particular, I think with recent work that my colleague Mary Lahan has been very much involved with, as have people from the Norwegian Geotechnical Institute, of gathering a lot of data on pile performance worldwide, but also looking at the different processes, and those processes haven't really changed much from the work, the project that Peter Roth initiated, that I was involved with in Cambridge, of separating out what happens during the installation of the pile, what happens during a period of reconsolidation of the soil around the pile, and what happens during loading of the pile. And so those are the three main steps. And then, of course, you've got the work of, again, Norwegians Alman Hamri and others who've focused very much on what they call friction fatigue or friction degradation, that the more you drive a pile past a particular horizon, the less resistance, shear resistance that you get as the soil remolds and destructures. So there's a lot of mechanisms that go on during pile installation, and not just offshore piles, of course, but any type of pile. And so I was trying to, in a sense, try to do a survey, a review, if you like, of where we sit between this hope to improve the algebraic solutions and the empirical data. And there are many aspects of pile performance that can be quantified. I mean, at the other extreme for particularly buildings onshore where you've got large groups of piles, you end up with a reinforced soil mass, or a soil mass reinforced by the piles, and it behaves in a fairly well-ordered way. Some survey of building stiffness and movement undertaken by the Italian group, Carlo Vigiani and Alessandro Mandolini, pointed out that actually the response of the building ties in very well with the small strain stiffness, Gmax, that you can get. So it's during operational life, it's an elastic problem, and so you can use elastic solutions for piles buried in soil to understand how the group will deform, allowing for interaction between the piles and so forth. So there are piling problems in spite of what happens during installation and the disruption of the soil, that eventually you end up with a system which behaves elastically. When a monopile is driven and then subsequently it's subjected to load, because of the restrictions on how far the pile can rotate, so the turbine stays basically upright, you're working in a largely not quite elastic regime. But elasticity of that, the solutions based on elasticity can work quite well for the operational conditions. And of course, you'd like to have a nonlinear PY curve that then takes you all the way to failure. But the failure event really is probably at a load that's 4 or 5 times the maximum operational load. So you're from a serviceability, you're working with quasi, I wouldn't say elastic, but of a smallish strain responsive of soil. So I tried in that, and I guess later with my McClellan lecture to sort of pick out some of the aspects that we can quantify and meet solutions for, and then what is the gap between those, what that might predict, and the actual response. And again, groups have worked on this. The Imperial College group led by Richard Jardine have made great advances in this area, as has my colleagues at UWA here. So I don't know whether we're closer now than we were in 2003. I think we are actually. We're quite a lot closer.
Yeah, we're getting there, and we still have a ways to go, but we're getting there. Yeah. Well, both of those papers from your McClellan lecture and your Rankine lecture are wonderful references for all of us, and particularly the young geotechnical engineers. So as we're closing up here, I want to ask you, what advice do you have for young geotechnical engineers just getting started in this field?
It sort of comes back also to the question of what attracted me to geotechnical engineering. Well, I suppose not so much I was attracted, but I warmed to it when I understood how the challenges involved in the topic. And I think for young geotechnical engineers in the field, it's it's a complex topic, and you start very green without any sort of limited background, however much you've had lectures at college. But I think the aim is to be motivated by the challenges, not put off them, and to try to understand the soil behavior as a mechanics problem, but understand what stresses and the soil is going to be subjected to, and how it's likely to deform. And you can't look up in a structures design manual what the solution is for a problem. And to me, that probably excites me. It fires me up to be interested. And I hope that young geotechnical engineers will feel that they start to think in terms of how soil behaves, what are the challenges, and to build a good interpretive model from their site investigation data, however sparse it is, into different soil types and how each of them are going to respond. I think to me as a profession, there are still much more variety. Every site is different in geotechnical engineering. As you know, every site has its own problems, whether it be from lack of data or from just the complexity of the site, and the challenges to come up with a building solution that is robust against some of the uncertainties that you have. There's a lot of work these days, which is not really my field at all, on probabilistic design, and I think that's a really good way forward to try to move away from deterministic factors of safety, much more towards the how safe are you in terms of what's the worst that can happen, what's the likelihood of a disaster occurring. And the other sort of advice that I would say is be skeptical, especially if you're a PhD student. Don't take anything that you read of my or other writings as at all gospel. I may indeed have changed my mind a year later from that paper. Who knows? So address it. Do you agree with the solutions presented? Can you reproduce them? Are you satisfied with it? Is the work correct? And once you've applied your skepticism, are you convinced? If so, move on to the next part of the problem. I think that's true for professional engineers as well. Don't just read up the code book and be lazy and think, well, does that apply to my situation? I've got a slightly different installation method for the pile. This is a drilled and grouted pile compared with a driven pile. What's the difference? And to make your adjustments with a in a thoughtful way.
Yeah, I think that's wonderful advice. And no matter how advanced the technology gets, the need for critical thinking is always going to be there for us as engineers. Okay, as we wrap up here, I want to ask you, for you today, what is a rose, a thorn, and a bud? And I'm not necessarily asking you this question in terms of your technical life or your professional life, but just you as a person, Mark Randolph. So let's start with a rose, something that's been successful for you recently. It went well.
It's hard to know. I think that my biggest rose is that I still enjoy life. I still enjoy the technical challenges. I'm comforted by the fact that the university centre that we started almost 30 years ago is still active and busy, and I go to uni once a week and catch up with colleagues there. So on the work side, I'm still stimulated, if you like, by new problems, and that's to me is important. Personally, a lot of our focus of people of my age go into our grandchildren, and we are so fortunate that of our two sons, the one that have had children, is based in Perth. Tom's got 3 children. Our grandchildren age from 14 down to 5.5, and so they're immense fun, and we have our whatever it is 20 years helping them grow up to be teenagers and beyond, and although they will then make their own way in the world, will have had a lot of enjoyment getting to know them. And of course, from a family side, I'm still really good friends with my wife. We get well together, and we still enjoy the same pursuits. We, go to exercise classes, Pilates in the gym, and we bushwalk or walk as much as we can. So that is great.
That's a bouquet of roses.
Yes.
Okay, now a thorn. So something that's challenging to you right now.
Well, thorns, yes. That I suppose inevitably, personally, thorns. There are looming health challenges that we fix a problem at a time, and hope that you don't get overcome by too many problems all simultaneously, which is so. And yes, we've had the occasional thorn. Touch wood, not too bad at this stage. But probably the biggest thorn, of course, is this are the newspapers and what goes on in the world, which I think is upsetting for everybody. And you can't just dismiss it and walk away from it. It does affect how you go about life. And I on the university side, I don't like the way the universities have changed over the last 20 years. I think they've become too corporate and too impersonal and uncollegiate, and I don't at all encourage young graduates, PhD graduates, to go into academia unless they really can't help it. So that's to me. I'm disappointed by that. So that's a thorn. And as I say, that there's no doubt that the world news and the effects of climate change that I think we're all feeling in terms of weather patterns and other things is the biggest thorn that we all face. It's nothing particularly personal.
Yeah. Okay. And last, a bud. So something that's got great potential that's you're excited about for the future.
It's the bud. I think I'm still trying to grow in terms of I've been learning Spanish for a few years, and I'm really enjoying that, and I enjoy the language side of it. I'm not very good at it, but that's to me is it's not going to change the world, but to me personally, that's a great joy. And I've grappled with the transition from Fortran to Python. As I use Python a lot these days, and I've rewritten many of my programs from Fortran into Python, because I think that's a wonderful accessible tool that is being used very widely. So to me, and that's a growth area of knowledge, which I think is so powerful. But that's so I think sort of summarizes what drives me through the day. But yes, I'm still eternally an optimist, which I think I see the glass half full.
Oh, that's wonderful. Well, Mark, it has truly been an honor for me to get to interview you. You are most definitely a geo legend, and I appreciate everything that you've done to advance our profession, and I look forward to still getting to interact with you in the future. Thank you very much, Mark.
It's been a pleasure chatting to you, Bob, and you've refreshed my memory of a number of things that I may or may not have said. But it's certainly a great pleasure to see you on the screen, and I look forward to seeing the final edited version of our interview together. It's been fun. Thanks very much.
Thank you, Mark. You have a wonderful day.
Yep.
Cheers.
That's it. Cheers, Bob. Bye for now.